Okay, so Newton's three laws are important to remember because usually at the beginning of a 10-mark question, say, often the first question will be, what is Newton's first law? Or what is Newton's second law? And that tells you what equations or what you're going to be doing for the rest of the question. So it's like when you ask the definition, it's a hint to the section that you're going to be doing in that question. And particularly with Newton's second, which actually is an equation, that's pretty handy. But let's go with the first one. So Newton's first law. I'm going to say it first. I'm going to do it like that. First.
Okay.
Not writing it. And the reason I do it is because this helps me remember the first law as a 1. And I think of that as an I for inertia. So this is the law of inertia. So inertia, if something is inert, it's not reactive, it's sort of staying in the same place. So this idea of something staying in the same place is the concept behind Newton's first law, is that if an object is doing something, it's going to keep doing that. So if it's staying in the same place, it's going to stay in the same place unless it's acted upon by a resultant force. Okay, so
oh yeah, I do remember that. Yeah.
Do you remember? As soon as you hear it, so this is
Yes.
sort of an object. This is how I remember it, but now you're going to go to your official definitions and you're going to learn the exact one, because we don't want to give them excuses not to give us the marks, right? So, but I'm going to say it as I kind of think of it, which is an object at rest or in motion. I would say remains at rest or continues in motion unless acted upon by a resultant force. So that would be a resultant force, or we could think of a resultant force as a net force. Okay, so this is how I kind of remember it. Now, when you look at your official definitions, it may actually be a little bit short and easy to remember, but you just got to remember it's inertia. It's that one. It's the one about an object being in motion or at rest.
Yeah.
And let's see why this is true. So it's when you throw, say, I know your dad said you played squash, but let's so let's think of a cricket ball. I'm going to use the idea of cricket in this because all of these laws, cricket's a good one to explain them. So if we have a cricket ball on the ground, if you throw the ball, you pick it up and throw it, it's going to keep going, but it eventually stops, which that doesn't agree with this, because this says it should continue in motion. But what's happening to this ball is you've got air friction. And so when you throw the ball, you release it. So at the beginning, it's in your hand and there's a force being applied, and then you release it. So now it's not being pushed by you anymore. So there's no force going and keeping it from moving. It's moving because it was already moving from leaving your hand. But it's slowing down because now there's a net force in the opposite direction, a law of friction, right? And so this is sort of a force diagram. So one of the things to remember is a force diagram kind of shows the cricket ball. And what's the other one called? The other diagram we have to know is the free body.
Yes.
Okay, so now we've talked about the three laws. The other thing you need to know is a force diagram and a free body diagram. And so if you were showing the ball when it's in motion, it's going to have friction going that way. So the free body diagram, once you let it go, is actually only friction in the direction opposite to the ball.
Yeah.
Of course, when it's in your hand, the net force is going that way. Because your body is, your arm is throwing the ball. Okay, but the main point of this one, Newton's first, I like to draw the first as a 1, and that reminds me of inertia, and then I think the body in motion. Because I'll be honest with you, I knew the laws when I went into my matric exam, and then I literally forgot them as I wrote the exam.
Oh, but sir, I'm grade 11 now.
Yes. Yeah.
Yes.
The point is that I never learned these laws. I learned these laws off by heart for the exam. But this system now allows me to teach you where I don't have to take a piece of paper and try and remember which one is which.
Yeah.
Because I remember the 3 laws this way.
Okay.
So that's the first law, is the inertia. Okay. So the second law, can you remember Newton's second law?
Oh, no, I don't think I can remember Newton's second law.
Okay, and like I said, I didn't learn mine until the night before the exam properly. And then when I left. But hopefully you remember the first law, inertia. And then that triggers your memory. Now you've seen pictures. Oh, I want to just talk a bit about the Newton's first. Another way I think of it as well. This cricket ball, when it's on Earth, slows down because we have air friction. Newton's first was much easier to understand in space. Because if you throw that ball in space, it doesn't stop.
There's no friction.
Yes. And that makes Newton's law much easier to understand. If you throw a ball in space, there's no friction, and so that ball just keeps going. And you see the things going around the satellites going around the Earth and all that. The only force the only power that those satellites are needed is the one when they start to fall, because the Earth is constantly pushing those satellites. So often they just need like a boost to get back up. So they'll gradually fall a little bit back down to Earth, and then there'll be a bit of power on the rocket, some thrusters, just to push that up into orbit. But it keeps going around, and that's no problem. It's because it's Newton's first. It is obeying Newton's first law. Okay, so then the second law I like to think of. I wrote Newton's law. Newton's second law. Okay, suppose we could think this is the one with the equation. So this is the one with the equation F equals MA. So the first law of inertia, second law is the one with the equation. Just the normal force equation. Because Newton's laws are all to do with force, right?
Yes.
Even the first one it talks about resulting force. So force is equal to mass times acceleration. Now, in order to do this law, what we have to do is to rearrange the equation to get acceleration. The subject of acceleration. So acceleration equals force, and when the mass goes to here, right? Goes to the bottom, goes to the other side. Just while we're here, important, you use triangles, right? You were showing from the beginning, right? So there's your FAM equation, right? Should have written the A before the M. Let's do that. The FAM equation. And then, so you make in order to remember the law, you first need to remember that it's just, and this is in your formula sheet. So you don't.
Yeah, it is.
So all we do is we go to the thing and we make A the subject, And then what we do is we say this in words. The acceleration of an object is directly proportional to the net force on the object, acting on the object. You'll say you'll check your official definitions, but this hopefully will help you to get the definitions in your head. Acting on the object and indirectly proportional to the mass. To the mass of the object. Okay, it's quite a long-winded definition. We kind of cover it. So let's think about this law and how it will apply to what you're doing. So we think about a car. I'm doing this because actually we were doing the cricket ball. Let's do the cricket ball. Okay, so let's say that you have a cricket ball that's 100 grams. If you have a professional cricketer who's much stronger throwing that ball, the acceleration is going to be much faster. Dale Steyn bowls the ball quicker. Why? Because he puts more force. The cricket ball is always the same mass, but Dale Steyn and the fast bowlers, the ball goes quicker out their hand because it's more force. So that acceleration of that object as it's going in the hand is directly proportional to the force applied. Okay, makes sense.
Yes.
Now imagine that ball was 5 times heavier, and you try to apply the same force. So Dale Steyn's got a ball that's 5 times heavier. It's going to be it's going to not go as fast because he's not going to be able to throw it as fast. So that's why it's indirectly proportional to the mass. And so one more thing I just want to show you while we doing this is we show this like acceleration is like this little fish sign, directly proportional to the force. And if we want to write it shorthand, that's how we say indirectly, because it's one. So as m gets bigger, the acceleration gets smaller.
Okay, that makes sense.
Cool. And the final thing is so that is Newton's second law. We just get that to we make the acceleration the subject of the formula. And once we have acceleration, then we find. So first law, inertia with an I. Second law, E, that's the one with the equation, the SE. Okay. Because first, second, third, none of those have an E. Second is the only thing that has an E in. That's why I remember that's the one with the equation. This is just this was to say my own way of remembering it. Newton's third law.
But isn't that like when Newton's third law is like when a object exerts a force onto another object, but that object exerts one back to the other one, if that makes sense?
Perfect.
Okay.
Yeah. So the third law is the one I think of that they quote in the movies. They often say every action has an equal opposite reaction. You do something to someone else, you're going to get a reaction.
Yes.
So, but as I say, I don't need to explain this one because you already remember it. So I'm not going to write it out. Newton's third law is an is exactly as you said. A force acting on an object, that object, the object, when a force acts on an object, that object exerts a force equal and opposite to the object, to the other object. So just you just get that definition from the book, or it's the exam guidelines. Do you have them?
We didn't get a demarcation.
Okay, I'm going to send you the exam guidelines for matric. That's the one you're going to learn. Are you doing the IEB, or are you doing the NSC? So it's basically the government paper or the IEB paper?
I believe it's the government paper.
Okay, because all the bishops guys that I taught when I was in Cape Town, they did the government paper. And you are at you in Stellenbosch, right? Or Paul?
No, I'm at Paul Boys.
Paul Boys. Okay. So look, it's all caps, so it's all the same thing. The only difference, I would say that the government paper is nice because it tends to put the questions in the same order every year. So Newton's third law, let's look at that, and because if it's true, so one of the questions, I don't know if you have the same one. One of the questions students ask me is, okay, if that's true, then if let's look at the cricket ball example. So if the cricket ball and a cricket bat, right? So let's look at okay, so you've got the cricketer holding the bat. And you've got the ball. If they acting in the same force, why does the cricket ball move there?
Well,
that's why that's what gets asked. So let's see if you could answer. Yeah, are you able to answer that?
Well,
we've got the cricket ball going there.
Since I'm gonna believe that since the like I'm gonna say, like, let's say the ball's object A and the bat is object B. So there's like already a force that's already going onto the bat, but so I cannot sort of explain it now.
Okay. So in order to understand why the cricket ball then moves backwards when he hits it, comes from Newton's second law. Because if these two have the same force, right? So let's do the force in light blue. So force is the same. These both have the same force. So F1 and F2 are the same. But what are their masses?
The masses, they would be different.
Yeah, so the mass of the guy's hand, so a bigger guy is going to be able to apply a better force. So we've got this bigger mass here, and then the cricket ball is 100 grams.
Yeah.
So if the force is the same, but this is 100 grams and this is, say, 15 kilograms, so that's now 1,000, that's 15,000. Look at the difference in mass, but they're the same force. And we know from Newton's second that F equals ma, and we rearrange that to have A equals F over m. So if the F is the same, if I put 15,000 here, the acceleration is much smaller.
Yes.
But now this acceleration here is going to be huge.
Yeah.
So
then the mass would be less.
Exactly. So, so this is how we can kind of understand it. The other way I like to think about it. So if that doesn't help, if I look at this wall behind me, and I say, well, let's think of the Earth, right? So this Newton's third law says that we exert the same amount of force on the Earth as the Earth does on us, which seems crazy because the Earth is massive, we small. How do we exert the same force? Well, this wall behind me currently is not exerting a force on me. It only starts exerting a force when I push. It pushes back.
Yeah.
So the force is dependent not on the wall, but on me pushing the wall. And so the wall's just going to match my force. So that's where Newton's third comes in. If you have a force being exerted, then you get the force being exerted back.
Yes.
Okay. Cool. So Newton's third, you already knew. I would say just now I'm going to stop the recording, and then you can go and you can write these three laws down and just try and remember them now. And just write them three, and then write those three, and those are key marks that you're going to get. And then if you ask Newton's second law, you're going to be getting this equation. Somewhere along the line, you're going to have to work out the acceleration, the force, or the mass. Definitely. If they ask you Newton's second law, this equation's coming 99% of the time. Okay, so and then because we'll get into momentum and the other forces, I just thought let's just get these three laws so that you understand them, and how mine. And then I'm going to show you something else now.